So hello everyone, my name is Sasha Ayun. I'm an eternal PhD student at Imperial College London. The work I'm going to present here is in collaboration with Xavier that just introduced me and is supervised by Filipa Garner and Petar Maksimovic at Imperial College London. I'm working on this for a while, so I'm happy to finally present here under heavy pressure from Xavier. And I'm going to talk about a hybrid approach to Rust verification. And what I'm going to start with is really what does that mean? What's hybrid verification? And why do we want to do this? And so in the last few years, there's been quite a lot of um, progress on Rust verification, starting in 2018 with Prusti, I think. Um, and there's all these tools now. So there's Creusot, obviously, Flux, Aeneas, Prusti, there's more. I'm not counting Verus here for because it's something slightly different, but it's what I'm talking about is really you write contracts and then you have a verifier that proves it more or less automatically. And for this talk, I'm going to be talking specifically about Creusot, but in theory, we could use other tools. I'm going to talk about Creusot. And so when you do verification using Creusot, you write a contract that looks like this. And this contract, without going into too much details and by simplifying just a tiny bit, this contract says that at the end of the function, the collection will be the same than at the beginning of the function, but with v added at the end. So when you push to a vector, that's what you expect, right? When you push, you expect that whatever you had before, you have the same thing, and then you have the new value at the end. But you'll notice that this specification completely abstracts over the real structure. For example, a vector may reallocate. So if your vector is full, then it reallocates, it copies everything, and then it adds the value to the end. But this specification doesn't say anything about that. And that's what's beautiful, really. It doesn't need to talk about it. And in fact, it will be the same specification if you specify a vector or if you specify a linked list. As long as it's a list-like structure, you can model it in the same way. The model of the vector or the model of or the linked list is the sequence of that. And that's really all you need to think about as a client. And the reason you can do that is because of the guarantees of safe of Rust. Um, and in particular because of the mutable reference. So if you're in C++, then when you push to a vector, you have to be thinking about, oh wait, this could be reallocating. So actually I need to think about that, the fact that if the vector was full, then now I need to get rid of my pointers and so on. But in Rust, because the mutable references are taking care of this lifetime management, you don't have to think about that at all. And specification can just be something about what happens to the vector when the mutable reference is over. And Creusot does this with this hat here, talking about the notion of prophecy. Um, and sorry, I was looking at the chat. So Creusot does this with the notion of prophecy. Prusti has its own version of doing this, and I forgot the name. But Prusti also does something to talk about what happens at the end of the mutable reference, and so on and so on. Aeneas also has these backward functions. So the main idea here, in specifically of Creusot, is that thanks to this prophetic reasoning, the the specifications exist in this world of pure representations. Um, and the world of pure representations is just what I talked about, this model. So the model of a vector is just a sequence of data, and it's the same model for a vector or for a linked list or whatever. And the cool thing, the cool side effect about this folder representation is that it actually makes analysis more efficient because you just have to think about this model and not about the intricate reasoning underneath. Therefore, safe Rust verification with Creusot is cool because you get easy to understand specification and you get easy to use specifications and they're efficient and so on and so on. And actually, you know what? Creusot is very fast. Creusot is very powerful. And Creusot has been able to verify uh, things that use higher order map operations in Rust, which I think nobody else has managed to do so far. So this encoding is really useful, but you cannot reason about the internally unsafe implementation of vectors or of linked lists. So Creusot will take the specification from this specification. Creusot will take the specification and just will have to assume this specification is correct. And that's a bit annoying because it means you haven't proven everything. But once it does, it's powerful and fast. So the solution here is obviously to write a tool that can do everything and handle unsafe code very well. And therefore you can just take all the other tools and put them in the trash and you're very good. Obviously that's not going to work. Why? Because these tools, as I said, these tools work because they leverage the invariants that are naturally enforced in safe Rust. And we have to remember always that 95% of the Rust code is safe. And therefore, if you try to apply a technique that verifies very, very tricky code, then you're kind of not taking advantage of Rust. And you're kind of just doing C verification. And obviously you don't want to do that. So the real solution is not to put all of the tools in the trash. The real solution is to verify, I mean, the solution we propose at least, is to verify safe and unsafe code separately using different adapted techniques. So for the safe code, use a safe Rust verifier. And for the unsafe code, you use techniques that are very well adapted to verifying unsafe code. And for us, it's going to be separation logic and so on because of Rust Belt. And this trick of doing verification separately for both for unsafe and for safe Rust, that's what we call hybrid verification. So let's zoom in. You have your safe Rust code, you have your unsafe library, and you have, let's say, Creusot that can verify the safe code. And so far, there's nothing that can verify the unsafe code quite in the way we want. So we develop Gillian Rust, which is based on the Gillian framework. I'm going to talk a tiny bit about it. But the important part is when you verify your safe code and your unsafe code separately, you need some kind of way to know that you verified kind of the right thing on both sides to get the guarantees everywhere. And so the glue really between the two worlds is the specifications. And you need both tools to agree on the meaning of specifications. And once you do that, then you can verify them, you can verify the two parts separately. So again, if Creusot works in this world of pure representations, then you need a way of connecting the real world. For example, for a linked list, you have this crunchy data structure of linked list that has all those pointers back and forth and so on inside. And you need a way of connecting the grungy real world to the world of pure representations. And once this is done, you can verify your code in Creusot and you can write your specification, your Perlite specification in Creusot. And then this gets encoded into a Gillian Rust specification, into a language that we call Gilsonite. The formalism that lets you do this is from Rust Hornbelt. I'm not gonna go into details, but this is basically what we implement into Gillian Rust to make it work. That and obviously adapting it to make it work in the real world. So the ultimate goal, that is still very much a work in progress, is to have one tool called Furnace, where you put your code that's annotated with both Creusot specification for the safe code and sometimes when you need them, separation logic annotations um, for Gillian Rust. And the front end would take care of splitting the code into Creusot and Gillian Rust by eliminating anything that the tool doesn't need or doesn't want. And then if both tools say that you're good, it's correct, then what about it functional correctness proof for the entire Rust code and not just the safe code or not just the unsafe code. And the goal is that because Creusot is very, very fast and very powerful on safe code, but GNRust can do efficiently, but not as efficiently as Creusot, but can do correctly the unsafe code, then you would have to put, let's say, more effort on the unsafe code and less effort, hopefully, on the safe code. And because there's a lot more safe code, then supposedly, as a whole, you haven't made that much effort. So the contributions here are Gilsonite, which is our assertion language and a set of traits and macros that we use to write contracts in separation logic. A way of modeling the Rust heap. I will explain why this is difficult. Techniques to automate borrow reasoning. A connection between Perlite and Gilsonite, so between Creusot and between the assertions language, the contract languages of Creusot and Gillian, and tiny proofs so far of linked list. We also have a tiny bit of vec, but I'm not going to talk about it. Right. So let's take a quick step back and look at Gillian, because I'm just going to say what you need to know about Gillian for this talk. Gillian is a parametric compositional symbol execution framework. Without going into too much detail, I'm just going to explain what compositional symbolic execution is. And that's basically symbolic execution plus separation logic. So you write contracts using separation logic. I'm not going to explain really what separation logic is, but all you have to know is that separation logic captures ownership. And so separation logic is usually what's used, well, since Ralph Young, it is what's used to reason about unsafe Rust. And computational symbolic execution tools, there's not just Gillian, but there's also, so maybe you know about Verifast, or maybe you know about Viper, which is the tool that underlies Prusti. And when you write when you use computational symbolic execution, the cool thing is that you can verify all your functions independently from each other. And it's pretty fast usually. Right. Yes, so as I said, separation logic captures ownership. And it's parametric in the sense that in our engine, there's a notion of state model, which is a parameter. And so, for example, there's a state model specifically implemented for Gillian Rust. And it explains how you interact with memory, with the state, so loading from memory, storing in memory, and so on. And there's a notion of also parametric logic. So you have the basic blocks of the logic. If you're familiar with this, there's the points to assertion. So the points to assertion doesn't have the same meaning, for example, in C or in Rust or in JavaScript. So we have different implementations of that. And if you're also familiar with that in Rust, if you take the lifetime tokens, for example, they would be part of these four predicates that you have to provide to Gillian. And when you do that, you also can implement a bunch of optimizations that are Rust specific. Optimizations or automations that are Rust specific. So the first part of this whole thing that we have to implement for Gillian Rust is the symbolic Rust heap. Right. So we want to reason about the Rust memory, obviously, because if you want to talk about the linked list or the vector and so on, you want to think about the memory, the heap, and what it contains. um, want to know how Rust thinks about the heap, because Rust doesn't think about the heap like uh like the physical heap it actually is, which is but just a bunch of memory. Rust has a memory model, and Ralph Young actually is working actively on this. Actually, Mini Rust was so he talked about Mini Rust in the past, which is kind of a specification of the Rust semantics and specifically of how the interaction of the memory works. Um, the work on Mini Rust was not introduced when I started working on Gillian Rust, but it turns out that the choices are mostly similar. And actually, since Mini Rust has been published, I tend to make the choices. I take Mini Rust basically as the source of truth, um, because I'm not the one deciding of the specification, and Ralph is much more closer to that, much more close to that. Um, oop, lost my video. But so Mini Rust is not enough because Mini Rust tells you how Rust thinks about the memory, but you still need uh, an implementation to reason about it in a verification context. So when you don't really know what the values are, when the sizes of the values are, when you have polymorphism, that's difficult because polymorphic means you don't know the size of the value, you don't know the type of a value. The other issue with Rust is that if you want a full correctness proof, you need to think about the fact that Rust does not guarantee any layouts. So in C, when you write a structure, then you know exactly what offset each field is. In Rust, that's not the case. Rust is allowed to do any optimization it wants, any reordering of the field it wants, any it can add any padding between and so on. So except if you write wrapper something, then you do not know what the representation of the heap is. So our solution to all these challenges is two things. First, we represent addresses, so pointers, in a layout independent way. And also we have two kinds of memory representations depending on if we know the layout or not. And they can communicate with each other. So without looking at the math too close, if you have two structures like S1 and S2, where S1 only has one field of type S2 and S2 has two fields of type I32 and I8, and then you take this address, which is the address of s.x.a offset by 4. So it's going to be 4 times the size of I32. Then we kind of keep the structure of the pointer like this during analysis. We don't compile it to any number or anything. We say it's some object, and we have taken the first offset of structure S1 and the second offset of structure S2, and then we have added 4 times the size of I32, and that's our pointer. So this first tiny trick uh, allows us to maintain a lot more structure and a lot more abstraction, and that allows us later to do some reasoning. Let's take, for example, um, a structure S with 2 fields. Then for that structure, we have to maintain kind of a tree-shaped structure because actually it has 2 fields X and Y, but there's many ways of representing it, and we don't know what Rust has chosen. The Rust compiler is allowed to make any choice really non-deterministically. There's no specification so far about what choice it's allowed to make when it's aligning the fields. So it can put Y first and then X and then some padding, or it can put X first and then some padding and then Y. The only thing it has to do is align each field correctly. But then it can make any choice. It's not even guaranteed that it's gonna make it's gonna make a choice that minimizes the size, even though obviously it does, but there's no guarantees. So when a structure is like this and we don't know what the representation is, then we only allow access through fields. So here I have access to the first field, then I can use this to navigate uh, this structure. And obviously, we keep the type of the structure everywhere so that we know that we're accessing the first fields of structure S1 or structure S2 because they don't have the same offset between the structures. The second kind of field of representation, memory representation is this laid out representation where, for example, an array of type of n elements of type T will be kept under this form where we have an indexing type and then we know we have each index. So here we have a vector V that contains k element of type T and the rest is uninit. So obviously that's a vector. So when a vector is partially full, then you have a vector, you have a list of values at the beginning, and then you have an initialized memory. So I showed this, but I'm not gonna go into too much details about how that's manipulated. But basically you can have fairly efficient reasoning about those structures while maintaining the abstraction. And that allows you to always be sure that you never do anything that is not illegal according to Rust. So basically, when you have a layout, then you're allowed to perform pointer arithmetics. But when you don't have a layout, then you're only allowed to do field accesses. And the second part, the second step, the second thing we have to implement is the verification of type safety. So what's type safety? Type safety is the guarantee that a function marked as safe can never lead to undefined behavior without unsafe code. So that's a bit blurry, but basically it's the thing that tells you that when you're doing Rust, if you never write unsafe, you cannot have any use after free or things like that. You cannot have any out of bound access and things like that that would be dangerous or really unsafe. So to walk through how we do this, and we're going to give a working example. We call this linked pair. It's really just a simplified linked list, because if you're talking about linked list, you have to handle the empty case, which is always annoying. Here, it's a linked list that always has two elements. Obviously, there's a cycle here in the pointers, because the first element points to the second and the second element points to the first one. And therefore, you cannot use mutable references. You have to use row pointers. And because you're using row pointers, you have to use unsafe code. There is an invariant reserve, which is this shape that, it has this cross shape, and the fact that it's not cyclic and so on. I mean, that's not cyclic in the sense this doesn't go back to the first node. So all those, so this looks very much like a linked list, and in a linked list, you really, really have to maintain this invariant, because if you don't maintain this invariant, then, for example, if you take this, where instead of having two nodes in memory, you have only one node, and this node, and both the head and the rear of the list point to the same node, then you would get a double free when dropping, because you would expect to drop the first node and then the second node. So when you break the invariant, you take a risk of creating undefined behavior. So what we want to do is be able to write show safety on top of a function. And we want a tool to magically tell us this function is safe. So let's try to do that. Can you see the code right now? Or can you still see the presentation? Just checking. Cool. Right. So the implementation of new looks like this in this linked pair. So you allocate the first node, you allocate the second node, you get the row pointers that corresponds to each node, then you create the link between the two, and then you return the structure that corresponds to this here. Actually, here. So you first allocate the first node, then you allocate the second node, then you create that link between the two, and then you return the pair of the two pointers here. And hopefully, if everything goes well, you run this, and Gillian Rust tells you, success, it's safe. Obviously, there's a lot of work to do to get there, but we're going to explain this slowly. So I'm going to explain what show safety is and what ownable is. Because in order to show the safety of something, you need it to be ownable in Gillian Rust. And what ownable is a trait that implements an predicate, which is the description of uh, of the invariance. So here, the answer here is described by, well, I hid it inside another predicate, obviously, but it says I have one node, I have a second node, they're separate in memory. This star says they're separate in memory, so you cannot be in the case where it's the same node twice. And it also says that the other fields of the node points to y, and the other field of the y node points to x, and then you own the value. Describe them. That's really exactly describing, again, this structure without going into details about the separation logic. So the first thing you have to do is describe the invariant of your structure. And to do that, we provide all those new cool things, which are a separation logic that is made for Rust. It looks a bit like Rust. You don't have to write too many type annotations. It supports polymorphism. In the linked list case, the values in the linked list are not monomorphized. Right. So I was saying the only new thing you have to learn about is this points to here and the star here. And star means it's separate, and the points to means really in memory it's that value. Um, and then show safety is just a macro that expands to the contract that says at the beginning of the function, if I own the value x, even if I own the value y, then at the end I will own the linked pair. And really that's just what we're doing here. At the beginning we have two values x and y, and at the end we have a self. And we've kind of lost the caller has lost the ownership of x and y, and this is what it's encoding. This is not my idea. This is all from Rust Belt, but yay, we can do this automatically because apart from the invariant, there's absolutely no annotation to add to this function. It's entirely automatic if you ask to show safety. And yes, that's the easy part because the hard part when reasoning about Rust, as we said, is reasoning about mutable references. So let's look at the assigned first function. Please bear with me, don't look at the math, but basically when you're talking about a mutable reference, now we need to talk about the ownership predicates, the ownable thing for the mutable reference, and it involves this horrifying thing called a full borrow, according to Rust Belt. And I'm not gonna go into details too much about what it does, but there's this even more horrifying thing written on the slide that I'm gonna hide behind cute crabs so that we don't have to look at it. But basically what it says is that while a lifetime is alive, a borrow can be opened to access what's inside. So if you take a linked list which has this invariance, and you want to add an element in front of it, then for a second you will have broken your invariance just while you're modifying the structure, while you're inside your function, you will have broken the invariance. And you are allowed to break the invariance as long as it is well formed when you close the borrow. And then there's this additional thing that makes sure that it's in this grab. No, I'm kidding. So there's this additional thing that makes sure that all borrows that you have opened, you have to close at some point, basically. And so we introduce another macro called hash borrow that you add to a predicate, and it makes this predicate a borrow. And it expands to something that looks like a borrow, but I'm not going to go into details into what it does. And for example, a mutable reference is just like a box, but it's a borrow of a value, not the value itself. And now if you want to assign the first element of a pair, if you want to assign the first element of a pair, then you first need to open the borrow, then you do your modification, and then you close the borrow. And because after modifying the thing, the invariant is still correct, then you've done your proof. The annoying thing here is that it's very annoying to write open borrow, close borrow every time you want to access a mutable borrow in unsafe code. You don't want to do that. So I spent a lot of time figuring out how to automate opening and closing borrows. I'm not gonna go into details because it's a bit complicated for this talk, but basically there's notion of guarded predicates, and the important thing about them is that Gillian and other tools really, but also Gillian already has uh, heuristics to open and close things, and I figured out a way to encode borrows into that thing that Gillian can already open and close without losing the correctness. And now this can be done mostly automatically. Well, actually, in this case, fully automatically. So if you take the assign first function here, and you run it, then GN will tell you that it verifies correctly. But if I was to, for example, let's see if this works. I haven't tried this before showing this to you. If I modify this to put a null pointer instead. So what I'm doing is I'm breaking the invariant by, instead of having this backlink here, I'm going to break this and put a null pointer instead here. And so that will break my invariant. I haven't tried that. Will it work? Well, yeah, failure. Obviously, I've broken my invariant, it fails. Right. But without this, it's a success. Um, Now, back to where I was, which was right after the cute crabs. Right, guarded predicates. Yeah, so now, great, we can do opening and closing borrows automatically, which is already a good first step. This next step is the problem of returning mutable references. So what's happening here, if you take the first mute, so it's equivalent to what happens in an index mute function in a vector, or really it's called first mute, I think, in the linked list, is you receive a mutable reference and you return a part of that mutable reference. So that's called borrow subdivision. And basically here, you're receiving a mutable borrow to the entire thing, and you want to return a mutable reference to just that cell here. So what do you need to prove? What you need to prove is that you can replace this Vx with any other value, and that will not break the invariance. It is when you Alban, I don't know what pronunciation it is, but it is when you close the borrow. When you close the borrow, the closing figures out that you haven't constructed the invariant back, and it fails. Sorry, for the recording, the question was what line causes the error? Is it when you write the null pointer or when you close the borrow? It's when you close the borrow. Um, right. So what we want to prove is that you can replace this with any value, because what happens is when you're executing this function, then the callee will receive a mutable borrow to the first element, and then you can use this mutable borrow to write any other value. So, and as this function does not have any control over what the callee will write, so this function needs to make sure that whatever is written using that pointer, whatever is written, you cannot break the invariance. So we need to show that we can replace this with any value. And the proof trick is to kind of instantiate a non-det node, which can, so there's a for all quantifier. So it says that for any other value, I can swap it with my value, and my invariant is still satisfied. That's what I need to verify. In this case, it's correct. And it turned out that there's another ugly math formula that allows me to encode this as a lemma. And then the proof looks like this. So what I talked about is this extract x function. Extract x really lemma. So you need to prove that you can extract this first node here without problem. There's another lemma involved that I'm not going to talk about too much, but basically the proof of first mute has two lines, the freeze thing and the extract thing. And it's always the same way you prove borrow subdivision. It's always freeze then extract. We've done the proof for vector. It's the same thing. You do the proof for linked list. It's also freeze then extract, and I will give an example later. But basically, you have this extract lemma here. So the extract lemma has a special macro called extract lemma. It has a specification, and then you can use it to prove first mute here. And actually, we also have second mute because it's it's just mirroring the same behavior. But then when you prove it, what happens is that first of all, it manages to prove it, second mute and first mute, but it also proves two new lemmas, which are this lemma, basically. The fact that you can swap the value. Gillian Rust is going to prove it for you automatically. And it actually also derives the lemma that allows you to do this. A tiny bit of real world thing, because I've been talking only about this tiny linked pair. I'm going to be talking about a linked list. Linked lists are infamously difficult in Rust because of the cyclicity and because the invariance that you have to preserve during verification. You have to prove the well-formed links, you have to prove the non-cyclicity and everything. But it turns out it's also famously easy with separation logic. So if you look at the new function, then it's here. We just have a show safety and it just works. If you look at pop front node, then same thing. Pop front just works. The only difference that we don't have closures yet. That will come very soon. So because we don't have closures yet, then we replace the call to map with an actual match statement, but it's the same thing. And so let me run this actually. If you run this, then it almost works. And then push front fails because it should fail, really, because push front will increment the length and the invariance, and this may overflow, really. Um, it's not really a safety issue because overflows are not unsafe, but it's still detected by our tool. This is something you should be able to configure, but so far, push front fails because it detects that incrementing the length may overflow. But otherwise, the proofs are really the same. And if you look at for front mute, it's the same blueprint. It's first you freeze something, then you extract what you need. And it's always the same. Right. The last part is functional correctness. And functional correctness is really the connection with Creusot because Creusot assumes type safety. So everything we've proven so far assumed by Creusot because Creusot only works on safe code. And the new thing now, functional correctness, is what Creusot proves. And this is what we're going to talk about now. So in Creusot, you have prophetic specifications. And the prophetic specifications use this model, really. Um, and for example, as I said, the model of a linked list is a sequence of values, not the linked list itself. And so what we do is we modify our ownable trait so that instead of having just the value, it also has the model. So now the ownable, the ownership predicate talks both about what the invariant of the structure is and what its model is. And that model really, really is the abstract representation that Creusot uses. So if you take the linked pair from earlier, then what you have to add, I'm actually going to show it here. What you're adding here is a model. Well, that's not here. You're adding a model and the type, the model of a linked pair is a pair of the models of the left-hand side and the right-hand side. And what you're saying, really, without going into details, you're saying that if the model of your left value is Vxm and the model of your right value is Vym, then your model is the pair Vxm, Vym, which is exactly what you'd expect. And then there's this way of encoding specifications automatically from Creusot to Gillian Rust, which is very much a work in progress. Well, we know how to do it, and then the automatic encoding, the implementation of the encoding is automatic. And to do the proofs, because I'm running out of time, and also because it's very complex, too complex for this talk, all I'm going to say is that we reuse concepts from the paper Rust Hornbelt that explains how Creusot works in the theory. And we implement them directly in Gillian Rust. If you want to talk about this, I'm very happy to talk about it. But there's concepts that are involved, like prophecy variables. A side note, here, I don't believe we could have done what we did without Gillian. I don't think we can automate to the same degree in other tools at the moment, but maybe I'm wrong. And also, in order to do all of those automations, we really, really had to push Gillian. So Gillian has improved a lot, both in the theory and in practice, thanks to this project. So yay, Rust. Right. And so let's look at quickly at the proof of a sign first. And so new just works naturally with the right specifications. And assign first has a new thing here, which will resolve the prophecy variable. I'm not gonna explain what that means in this talk, but I believe it could be automated. And what it's really doing is there's this ghost state capturing what the values of the prophecies are, the Creusot prophecies. And it's imperatively updating this at the right moment. I think it could be automated. But let's run it just to make sure it still works. Uh, ah, no, wait, what? Ah, I forgot to run this before. Yay! And first mute fails for now. Because that's basically future work, which is for now. Ah, that's gone from here. Yes, so we don't have returning mutable references completely working at the moment with prophecies. Uh, that should be in the list of future work, but this is coming extremely soon. It's already on paper, and now we just have to implement it. Otherwise, in the rest of the future work, we need the compilation from Creusot to Gillian to be automatic. Right now, we do it by hand, but we do it in a systematic way. The evaluation is very limited. We've only done a bit of linked list, a tiny, tiny bit of VEC. Our goal very, very soon, like in the next month, is to improve the evaluation. The encoding of lifetime is not great because we're not using Polonius. We're not extracting the right information from the compiler yet. The Ghost code implementation is not great either. And we don't support anything like stack borrows, tree borrows. We don't do multi-crate analysis. There's a Obviously this is very, very much a prototype, but there's a few things we're going to improve soon and a few things that we don't care about so much right now because we still at the proof of concept stage. Right. Any questions? Florian, how inter how interoperable is Gillian Rust with Gillian C? Could you also verify specification across language barriers? That is a very interesting question. Um, the answer is right now, not at all. Uh, I have thought a lot about FFI using Gillian. I very much think it is possible using the exact same approach we use between Gillian Rust and Creusot, which is the interface is at the specification level. So what you really need to do is be able to interpret the Gillian C specifications in Rust, and then you would be able to call C code from Rust. And then you can verify separately. GNC verifies GNC and GNRust verify GNC verifies C and GNRust verify Rust. In theory, that's possible. I haven't done it yet, and that's probably not happening anytime soon. But yes, in theory.
All right, thanks for the talk. Quick question. So as far as I know, Gillian is a sequential separation logic. So I guess the question is like, what is the type safety proof caveated under with respect to concurrency? Is it that like I didn't implement send or sync or anything like that? Um, in that sense, since there's the type safety proof isn't reasoning about concurrency.
In fact, the type safety proof is reasoning about concurrency. Uh, because the proof is really automating a RusBell proof. Um, I cannot, so I haven't verified anything or I haven't aimed to verify anything very, very concurrent yet. But in theory, GDN is very much concurrent in the sense that the specifications are separation logic and therefore they apply to concurrency. We have had students working on concurrency in Gillian and it just works. Um, we don't verify things. So if you wanted to verify that something is sync, then you would need to prove additional lemmas. But in theory, that's not impossible with Gillian, if that makes sense.
Yeah, makes sense.
Cool.
Oh, I have some questions. Also, I don't know how good this mic is. How
Good enough.
can
We
you?
can hear you.
Okay, okay. So I was wondering, what kinds of things can one prove with separation logic in general? Um,
What?
I sort of know, but I don't know like the concrete examples. Um,
So what kind of things you can prove with separation logic? That's the
hmm,
question.
yeah, yeah.
Um, it's a difficult question to answer. It's very general. You can prove many things with separation logic. I think most things that Rust. The big question is what can't you prove with separation logic?
Hmm,
You can't easily reason about hyper properties, so you can't reason about, I don't know, how long something takes to execute. Well, not easily, at least. You can't reason about some kind of like side channel attacks using separation logic. Uh, but anything that's like functional correctness, usually separation logic can do. I feel like that was a terrible
nice.
answer.
No, no, no. That was actually really good. I think that sort of gives me a kind of validation that perhaps we still don't have uh, like concrete tools with which to reason about side channels, for example.
Yeah.
Um, no, but what I am, I should have phrased my question better, but um, what I wanted to what I wanted to know was like in separation logic itself, like so say with first order logic, I am able to prove. Oh fuck me! I don't have piano arithmetic in my head all the time. But like okay, so say with proposition logic, you can prove the compactness theorem, for example. What kinds of theorems appear on the table when you start using separation logic
So the
in
thing
that
is,
sense?
separation logic is technically I hope I'm not saying something dumb, but I believe it's a superset of first order logic. Um, it's
That makes sense.
it's mm, it's not more expressive, but it's much easier to manipulate when you want to reason about mutating the heap, and in particular when you want to reason about ownership of the heap, which is what Rust is doing. Um, I hope that makes sense. So yeah,
Yeah.
you can prove the same kind of properties.
All right. Nice. Cool. Thank you so much.
Perfect.
I am really glad that Florian is. Oh, that's really cool. Oh, okay. I am not super versed in anything beyond like first order if maybe, but okay, I will look that up. Thank you, Florian. And I said this in chat, and I will shut up after this because I'm taking too long. Um, thank you for your work on this because I think formal verification is really cool, and I have tried to learn it twice. In first with Idris, and then with C, like verifiable C, and like it's either the tooling is bad or C is just too daunting in the formal verification space, and being able to get the sort of certainty that I want with something like Rust. That is so awesome. Like thank you so much. Like,
Pleasure. And there's a lot of people in this call working on this also. So
oh,
let's hope
thank you to all of you. Okay,
Thank you very
that was
much.
all I have. Thank you.
Thank you, Felix.